Hi, everybody. This is Miss Kabani from Saxe High School. Today we're going to be talking about Dalton's law of partial pressures. And basically, what the law says is that the total pressure of a system is equal to the sum of the partial pressures of each gas in the system. So basically, what that means is these gas molecules are all in the same tank, but they're all exerting their own kind of pressure. And if you want to get the total pressure of the system, all you have to do is add them up. Now, there's going to be a twist to Dalton's law in a second when we say that a gas has been collected over water. So we're going to have to take into account the vapor pressure of water at that temperature. But really, this is one of the more easier laws. It really takes into account, okay, well, all these gases are exerting some kind of pressure. What is the total pressure? Okay, so that's what's going on in the first one. You have oxygen, helium, and nitrogen. Oxygen is exerting 35 atmospheres. Nitrogen's exerting 5. And helium is exerting 25. Okay, so the total pressure is the sum of all of the partial pressures. Okay, so 35 plus 5 is 40, plus 25 is 65, and our unit is ATMs. Okay, same thing with the next one. This time they give you the total pressure. And then you have to find one of the partial pressures, okay? So they're saying blast furnaces give off many unpleasant and unhealthy gases. If the total pressure, so we have P total, is equal to the partial pressure of carbon dioxide plus the partial pressure of hydrogen sulfide plus the partial pressure of air, okay? They want to know what is the pressure that air is exerting, okay? So I have my total pressure is 100.3. The pressure of carbon dioxide is 5.07 kilopascals. And the partial pressure of hydrogen sulfide is 2.03. So I'm solving for the pressure of air. Okay, so what we're going to do to solve for the pressure of air is we're going to add these two up and subtract it to 100.3. So we're going to get the pressure of air by itself. Okay, so I'm going to do 5.07 plus 2.03, and that's 7.1. And then I'm going to subtract 7.1 to each side. And the pressure of my air is going to be 93.2 atmospheres. Okay, so here they give you the partial pressures of all the gases in the tank, and they're saying what is the total pressure of the tank, and we solved for that by finding the sum, so just adding. Okay, but here they give you the total pressure and they're looking for a partial pressure of one of the gases. So again, all these can be solved with algebra if you don't have, all the partial pressures given like the first one. Like this would be a very simple example. Other ones you would have to kind of look a little harder, read a little more carefully, such as the next one. Okay. Now what I mentioned at the beginning of the video is anytime a gas is collected over water, we look for something called water displacement. So basically, if you have a reaction that's happening in a tube and that tube is placed in water, the gas that is forming is going to essentially push out the water. And if you notice how much of a gap has formed in the tube, that's how much gas has been formed. So we're really interested in, okay, not only is the water not in the tube anymore, but what has formed is a gas. Okay, so an example is if you have zinc plus hydrochloric acid, it's going to form zinc chloride and hydrogen gas, and that hydrogen gas is going to form on top of the tube, and you can actually measure how much gas has been collected. Okay, so one of the reasons why it's important to know what the vapor pressure of water is because we don't want to account for the pressure of water. We want to just account for what the pressure of the gas is. Okay, so we have to look at what temperature the gas was collected, okay, and look at what the vapor pressure of water was at that temperature, okay, and this is our vapor pressure table. So here they give you, you know, all these different temperatures, and then what is the respective vapor pressure at that temperature. Okay, and in this case, if it is collected over water, you're going to look for these three magic words. Okay, if it is collected over water, you're simply just going to subtract the pressure of water. Okay, so let me do an example with you guys so you can see what this means. All right, so it says when hydrogen gas is collected over water at 20 degrees Celsius, the total pressure was measured at 756. So if I have the equation P total is equal to the pressure of gas plus the pressure of water, okay, my total pressure is 756. The pressure of my gas, which is hydrogen, I don't know that, okay? But I have to look at what is the vapor pressure of water at this temperature, okay? So I'm going to look at my vapor pressure table, and at 20 degrees Celsius, the vapor pressure is 17.5. So that's my pressure of water. Okay, now to get the pressure of hydrogen, essentially this is our gas, hydrogen gas by itself, we're going to subtract 17.5 to each side, and therefore my pressure of gas, okay, we're going to do 756 minus 17.5, and that's going to be 738.5 millimeters of mercury. Okay, so again, the whole idea is that we don't want to account for the pressure of water. I'm more interested in the pressure of the gas that was forming. So we just had to subtract the pressure of water. And at different temperatures, there's different pressures, which we know from Boyle's law. So we have to take that into account. Okay. When oxygen gas is collected over water, the total pressure at the time was 1 atmosphere. Okay, well, 1 atmosphere, this is a standard unit of pressure. 1 atmosphere is equal to 760 millimeters of mercury. So look back at your STP notes, standard temperature and pressure notes. Okay, 1 atmosphere is equal to 760 millimeters of mercury. And the reason why I needed to convert that is because this vapor pressure table, all the units are millimeters of mercury. So if I use atmospheres, that's not going to help us because they don't match. Remember, you want to be very consistent with your units. Otherwise, it doesn't really work out mathematically. Okay. So I know my total pressure. Okay. They want to know what is the partial pressure of oxygen. And since this was collected over water, I have to take into account the pressure of water at that temperature. Okay, so I know my total pressure is 760. My pressure of oxygen, I don't know that yet. Okay, now for the pressure of water, I need to look at what is the pressure of water at 40 degrees Celsius. Okay, so at 40 degrees Celsius, the pressure of water is 55.3 millimeters of mercury. So I'm going to put that here. Okay, and now algebraically to get the pressure of oxygen by itself, I'm going to subtract 55.3 to each side. So 760 minus 55.3 is 704.7 millimeters of mercury. Okay, so this is kind of, you know, one of those that you really have to pay attention to what's happening at this temperature. We're being able to refer to this table is another skill. This is not something people memorize. This is a reference material, so this is something that you would have been given. Um, but you just have to have the wherewithal to be like, okay, well, if it's collected over water, I need to know what is the vapor pressure at this temperature. Okay, and then just solve from there. Notice I just took the total pressure and I subtracted the pressure of water, and that got me the pressure of my gas.